Okay, picture this for a second. You're an explorer, right? You're standing on the edge of this massive, totally uncharted digital ocean, and your mission is to map every single landmass you can find. Well, that's exactly the mindset you need to conquer one of the absolute most famous algorithmic challenges out there, the Count Islands technical interview question. Welcome to this explainer. Today, we're not just going to memorize some code and hope for the best. No, we're going to build a rock-solid mental framework so you can walk into that interview and ace this challenge with total confidence. So, let's dive right in.
Here's our roadmap for today. We'll start with the Count Islands challenge itself, see why grids are actually graphs, explore with depth-first search, look at the full matrix strategy, and wrap up with some performance and interview tips. All right, section 1, the Count Islands challenge. Let's look at exactly what we're trying to solve here. So here's the classic setup they're going to hand you in the interview. It's a binary matrix. The ones represent land, and the zeros represent water. Your overarching goal is super simple to say, but a bit trickier to actually code. You just need to return the total number of distinct islands. Like, if you look at this specific example, you can pretty clearly spot exactly 2 distinct islands floating out there in the water.
But wait, what actually makes an island in this context? According to the rules, an island is formed by connecting adjacent lands. Those ones, strictly 4-directionally. We're talking up, down, left, and right. That's it. If you've got a one that's diagonally adjacent to another one, no way, that doesn't count. They do not connect. It's a strict vertical and horizontal bond. You've got to keep this rule in mind because it's literally the foundation of how our algorithm is going to move.
Moving on to section 2, grids are actually graphs. To solve this, we kind of need to flip our perspective.
Before we try to count, a dozen islands across a massive board, let's just isolate one. If we read this matrix like a book, starting top left at 0, 0, the very first land cell we hit is at row 0, column 2. From this starting point, we want to find the rest of the island. But think about it. How does the computer actually understand that the one right beneath it is part of that exact same structure?
Okay, this right here, this is the massive aha moment of the entire problem. Every single land cell on the same island is accessible by moving horizontally or vertically, right? So conceptually, this rigid grid, it's actually just a graph. Each one is a node, and every adjacent connection is an edge. And honestly, once you see the grid as a graph, everything clicks. You realize you don't need some weird custom grid-solving trick. You literally just need a standard graph traversal algorithm. Which brings us to section 3, exploring with depth-first search. Now that we know it's a graph, how do we walk it?
So we're walking around this graph, but how do we stop ourselves from walking in endless circles until the interview timer runs out? We have to leave a trail. We have to mark where we've been. Now, you've got a choice. Option 1, use a separate data structure, like a hash set, to track the coordinates you visit. The problem? That eats up extra memory. Option 2, and this is the smarter play, modify the matrix in place. We just change the value of a visited land cell from a 1 to a -1. We're essentially sinking the land right behind us, so we don't ever step on it again. It's brilliant, and it saves us valuable memory space.
Let's see it in action. We kick off our depth-first search, or DFS for short, at that first cell, 0, 2. We immediately mark it as visited by changing it to a -1. Now, we look around 4-directionally. The only neighboring land cell is directly below it at 1, 2. So, our algorithm steps down to 1, 2. Following our golden rule, we immediately mark this new cell as -1. Then the algorithm checks 4-directionally again. Above us is a -1, so nope, we don't go there. But to the left, there's another one at coordinate 1, 1. So we make a recursive DFS call and jump over there. We land on 1, 1, and boom, change it to -1. Now from here, we actually have 2 choices of neighboring land. We've got one below us and one to the left. Since this is a depth-first search, it's just going to pick one and keep plunging deeper. Let's say it decides to explore this cell to the left at 1, 0 first. We mark 1, 0 as a -1. But look around now. Water, water, edge of the board, and a visited -1 cell. It's a total dead end. And you know what? This is exactly where the magic of recursion shines. Because it hit a dead end, the algorithm naturally backtracks to the last cell that actually had unexplored options, which was 1, 1. And then it travels down to explore that final piece of land at 2, 1, marking it -1. And just like that, the DFS is completely done. The entire single island is now marked as -1. And why is this absolutely crucial? Because when our main program continues scanning the rest of the board, it's just going to see these -1s as water. There is 0 chance it'll accidentally count this exact same island a second time.
Section 4, the full matrix strategy. We mapped one island,
So let's zoom out and map the whole ocean.
Here's the master plan. These are the 4 overarching steps you're actually going to write in your code. Step 1, search the matrix cell by cell, starting from 0, 0, until you find a 1. Step 2, pause the search and trigger your DFS function to explore and sync that entire island to -1s. Step 3, increment your island counter by 1. Step 4, resume your search exactly where you left off until you hit the very end of the matrix. Watch how this flows. As our algorithm sweeps across the board, it finds the first island, runs the DFS, and our count goes up to 1. Because that first island is now completely sunken into -1s, our search safely ignores it. It just keeps scanning row by row until it hits a brand new one. Boom, it triggers DFS again, syncs the second island, and the count bumps to 2. By the time it finishes scanning the whole board, we've got our final correct count. Now, from a strictly coding perspective, how do we elegantly tell the computer to check up, down, left, and right without writing a million messy if statements? You use an array of direction vectors. It's usually called dirs. It's just a simple list of coordinate modifiers. By looping through this array and adding these values to your current row and column, your code cleanly checks all 4 adjacent neighbors. It is such a clean, pro way to structure your logic. All right, final section, section 5, performance and interview tips. Because nailing the code is only half the battle. You know for a fact they're going to ask for your big O complexity. For this approach, time complexity is big O of m times n, where m and n are your rows and columns. Why? Because you visit each cell at most twice, once during the scanning phase and maybe once during a DFS traversal. It perfectly scales linearly with the grid size. Space complexity is also O of m times n. Why? Well, even though we save space by dropping the hash set, the recursive DFS call stack itself could, in a crazy worst-case scenario where the whole board is just one giant squiggly island, grow to the size of the entire matrix.
Okay, before we wrap, I want to drop a massive behavioral tip for you here. Notice how our strategy modifies the input matrix by changing 1s to -1s? Well, in the real world, mutating input data like that can sometimes cause totally unexpected bugs in other parts of a system. So before you start coding this highly efficient solution, just pause and ask the interviewer, hey, are modifications to the input acceptable? I'm telling you, asking that one simple question shows incredible professional maturity and situational awareness. They love to see it.
So what's the big takeaway? Once you unlock this perspective, the realization that a boring grid of numbers is actually just a hidden graph waiting to be explored, a whole new ocean of algorithmic problem solving opens up to you. So, my intrepid explorer, what other grid problems will you conquer with this new mindset? Take this framework, apply it to your very next coding challenge, and honestly, I think you're going to be amazed at just how quickly you find the solution. Catch you next time.